quizzes, past quizzes out there. So if you're missing one, you can go up there and get it. It should be there. And please don't take somebody's unless you're told to take somebody's, because students expect to find a quiz and somebody's taken it and they didn't know it. And it happens. All right, so if there's any questions about the radar stuff, you know, I put a bunch of problems up there with solutions, right? Did anybody have any questions at all? You have one? No? Okay, we're good. All right. I'm happy. If you're happy, I'm happy. Yeah.
I just have a small question. When it says the sigma value is 0 dBm, is that just 1?
Whenever you're talking about dB, it's related to power. dB in general, let me just go through this with you. Now, this is important because people mess this up and they're almost afraid to ask about it. When we talk about decibels, if it is a power-related term, it's 10 times the log of the power-related term. Now, gain is related to the power, so it would be 10 times the log of the gain. Now, I'm going to just go through this. This is dB for power. Is there a waste can back there? No, nothing. All right, well. This is for power. When you talk about power, most of the time they do it by talking about something that's called the normalization relative to something. So the term dBm is often used. That's dB, where the power itself is divided by 1 milliwatt. And that's 10 times the log of the power term divided by 10 to the minus third. Because 1 milliwatt is 10 to the minus third. Now, dBm is a very common unit. How many have heard of this? Most of the time, when you see power measurements done related to like cellular activity and stuff like this, the expression will be given, or the quantity will be in dBm. That's almost guaranteed. And this is power. When you're talking about voltage or current, dB, if you're talking about voltage, is 20 times the log. And this is log base 10, by the way, not base E, of the voltage. This would be V in dB, sorry, voltage in dB. And it's either voltage or current. Or current. What's really common when you're talking about a voltage decibel measurement is called the voltage in dB microvolts, or just put micro. Usually, sometimes you do UV, and that's 20 times the log of the voltage over 10 to the minus 6. Y'all follow? And dB microvolts are used all the time in measurements, especially when you're dealing with things related to cellular activity, cell phones, Wi-Fi routers and stuff like this. Almost always dBm and dB microvolts with voltage or power. Just remember that. Now, when you talk about radar cross-section, because it's related to power, dB, and it would be square meters usually, where the quantity here will be dB square meters. That's 10 times the log of the quantity. In this case, it's cross-sectional area, right? It's sigma RCS. Y'all follow me? This would be sigma dBm. Now, 0 dBm, we put a 0 over here because it's given in dBm. 0 would be 10 times the log of sigma RCS, right? Divide 0 by 10, you get 0, right? Take it to the 10th power, take 10 to that power. So 10 to the 0 is 1, which is sigma RCS, and that's the linear value. But believe it or not, this stuff I'm showing you, if you just give a standard junior in engineering, any doesn't matter, well, junior in electrical engineering, you'll find out there'll be about 15 to 20% that will have trouble with this. And it's my estimate at least, based on past. They won't know this stuff. And I'm not sure if they forgot it or never really understood it to begin with. But are we clear on that? Now, the question all about the radar stuff?
Actually, could you just do the first one? It's intensity of transmitted EM wave at a range of 500 meters from the radar.
Well, yeah, give me that, what are the parameters?
We have, it is, PT time, oh wait, sorry, this is what it is.
What's the transmit?
It's K, 0.4, or sorry, 0.0025 watts per meter squared.
That's the power density. Can
Sorry.
Good, well, good.
So it's the intensity of a transmitted EM wave at a range of 500 from the radar.
Alright, so you're at a range R and you have an average power density given, the average here, and it's, what is it, 0.04 watts per meter squared, alright? Now, this is, just checks to see if you have a good understanding of radars, or really power transmission in general. We know the average power density from any kind of antenna will always be the total power transmitted over 4 pi r squared. That's where I always start. That's isotropic, no gain, no focus. Then you multiply by the antenna gain, and that's the power density at the point, right? So what they give you is this, and if you look at this for a second, all this stuff is one big constant. Do you all see that? It doesn't change no matter how far away you go, as long as you don't move your azimuth or elevation angle. So I can just put it as one constant, K, over R squared. Now, in our case, we know what it is at a certain range. We know it's 0.04 at a range of, and if you look at this, what is it? I forgot the distance.
5 kilometers.
5 kilometers?
500 is the first.
500 meters, yes.
All right, so it would be divided by 500, right, squared. Right, that means K itself is equal to 0.04 times 500 squared. Y'all agree with that? From that point on, at any distance, I can tell you what the average power density is, because I have K. I have this constant, which is all this stuff. You follow me? Everybody follow me on this one? All right. So then they ask for it at what? They want the average power density, how far away? That's general EMAG, by the way. What range?
2 kilometers.
All right, so now I put in K, which is 0.04. Then I put 500 and 2,000, right? Divide this by 2,000 squared, because really it would be 0.04 times 500 squared, then divided by 2,000 squared. Do y'all agree with this? You can see one thing that should be apparent. When I look at this, I really have 5 over 20, or 1/4, right there, right? When I square that, that's going to be 1/16. Do you all agree with that? That means this, the power density that far away, is going to be 0.04 divided by 16, or only 1/16 the power density it was at 500 meters. The real thing about this is power density falls off, it's proportional to 1 over r squared. That's one of the things you should at least appreciate about this. With radar though, the power return is proportional to 1 over r to the 4th. It really falls down quick, all right? Radars, you don't get much back for the amount you send, almost none. Okay. Any questions? Any other questions? And that's generally, that's just basic EMAG. It's nothing really directly related to radar, but.
Yeah, I think I just misunderstood the solution, but okay, I got it now.
Okay. Next, we're done with chapter 8. We're into chapter 9. This is EMC. Now, I'm going to try to teach EMC from the perspective of what would really be beneficial to you. There's a whole lot of aspects to EMC, and some of which are kind of, I think you have a small chance of really running into those situations. But the whole thing with the way Dr. Wentworth presents is, first he's presenting the most practical things that you should be aware of if you're doing electromagnetic compatibility engineering, and it always has to do with high frequencies. So they start with what a wire looks like at high frequencies. So if you think about it, a wire itself, if you got a wire of some length L, right, well, let me use this symbol for length. And the wire has a radius A, it has a conductivity sigma. If I wanted to measure the resistance between the ends of the wire, here and here, I wanted to know what the resistance was there. I know, I mean, the way you're taught to do this back in EMAG 1, you assume a current, right? Then you assume a uniform current density across the cross section, so it'd be J would be, I'll just go through this with you. Normally what you do, if you want to find resistance, is you assume a current I. So from I, then you get J, that's the current density, that's I over the cross-sectional area, which is pi A squared. Y'all with me on that? That's J, and J is equal to sigma E, right? I'm sure you guys remember doing this, right? It's jogging your memory, at least. Then after you get E, which E of course would be equal to J over sigma, it's equal to I over pi A squared sigma. Now, you find the total voltage from this end to that end. Y'all follow me on this, class? Remember doing this? And the voltage itself, you can do as a magnitude integral over the length from 0 to L of E dot BL. And that's really because the E field's a constant. It's just going to be equal to the actual value of the E field, which is I over pi A squared sigma times the length L. So now I've got the voltage, I assume current, I end up with the voltage, then I get the resistance R, and R is equal to voltage over current, and you can see I just get rid of the I, and that means it's L over pi A squared sigma. Now the real thing, and I try to really make sure you understand, regardless of the cross-sectional shape of the wire, if it is a constant cross-section, and it doesn't like blow up like an actual conic section or something, then what you really have here is the length proportional to length, inversely proportional to cross-sectional area, and inversely proportional to sigma. That's the general form of resistance. But that would be the DC resistance, because we've assumed that the current had no time variation and was uniformly distributed. Now, y'all remember when we said what skin depth did? Right. Skin depth caused all the current to hug the surface of the wire. And then you have what's called R, and I like to call it R high frequency. I think in Whitworth's book, Dr. Whitworth calls this RAC. Now you're talking about now when you have a time varying or alternating current that's high frequency. And the first thing you do is check the skin depth, which is equal to 1 over the square root of pi F mu sigma. And if the skin depth is less, it should be much less, but is much less than A. In other words, the radius is a lot bigger than the skin depth. Then the surface of the wires where all the current's going to be kept. There's nothing going to be internal really. And now you can find that RAC is still going to be proportional to the length, inversely proportional to sigma. But now the area that the current goes through is just around, it's just going to be 1 skin depth deep. If the radius of the wire is A, you can see if you just cut that and spread it out, the total length here would be the perimeter, or 2 pi A, and this width would be a skin depth. Can you all imagine that, guys? Take a good look and just let it sink in, right? Remember going through this before, everybody? All right, now that means the area itself is skin depth times 2 pi A. We could do it another way, but this is the easiest. So it's 2 pi A times the skin depth. And that's the AC resistance. And I'm just going to leave skin depth there. We could play with this and change it a little bit. That's it. So RAC, if the skin depth is much less than A, is given by that. Everybody agree? Now, there's another thing that happens. So the wire at high frequency doesn't have the same assumed resistance it does at low frequency. As a matter of fact, the resistance can be very, very high, depending on the frequency. When you get to 50 gigahertz and stuff, a small diameter wire can have a lot of resistance. Usually what they do is have hollow piping, because they don't need a solid piece of copper. They need just the shell on the outside, because that's where all the current would be developed anyway. There's a second thing that happens. The self-inductance, or the internal inductance. Remember, the symbol for inductance is L, and I'll call it LDC, and I'm going to do this in a per meter, so I don't have to do it in terms of length. Well, y'all remember how we calculated DC, or you calculated it one time, back in the day when you had EMAG 1. Anybody have me for EMAG 1? Oh, you did. And you, all right. Back in the day when we calculated the internal inductance, it's really associated with the energy inside the wire core. You remember that? Most of the energy actually is outside, or the inductance of a wire is actually related to the energy outside the wire. But the internal inductance is important. It's important to understand this and actually calculate it. So the internal inductance is the way you found it. You assume the current, right? Then from the current, you assume that you got J, which is I over pi a squared. After J, then you had to calculate H using Ampere's law. Now, I'm not going to go through all this, but it would be the integral of H dot dl, or 2 pi times the radial distance times H, was equal to the current inside that, which was equal to J times the area, or is equal to I over pi a squared times pi r squared. And then you messed with that, and then you found the H field. Once you had the H field, then you got the magnetic energy density was 1/2 mu H squared, right? And then you integrate the energy density over the actual volume internal to the wire, and you set that equal to 1/2 L, the inductance I squared. Y'all remember this? The I squareds cancel. And then you get an L. And the one thing about L, DC, does anybody remember the one unusual thing about this? This is the per meter. It was proportional to mu, right? Or mu naught, mu relative. But then instead, and then it was just divided by what? 8 pi. Y'all remember that? There was no geometric factor. It didn't matter what the radius was. The only thing that mattered, in truth, is that you had a wire that had a uniform current distribution on the inside. That's it. So that would be the DC inductance per meter, internal inductance. Now the internal inductance, LAC, or high frequency, I'll put it HF. And this is when the skin depth, again, is much less than A. That's going to be proportional LDC, but then it's multiplying that by 2 times delta over the radius A. Now, we can go through this one if you want the proof for it, but here's what he's really doing. He's assuming all the current is going to be distributed over one skin depth. And then he finds the internal, he gets the magnetic energy density in there, integrates it and sets it equal to 1/2 Li squared, and then you get that L value right there, AC. Do you follow me on this class? We can do the formal proof, but it's better that you look at this on your own when I give you an assignment. So this would be high frequency DC, or high frequency internal inductance. If you have your books, anybody? If you look in your books in chapter 9, you're going to skip through, it's in the first page. Let's see here. I'm not sure actually the page it's on, but you'll see something where it has L, and it will say either HF or AC. You see it? Anybody? It's chapter 9. Flip that page. There's L, DC right there, and that's AC. See? Okay, what he does, he's equation 9.6, but he doesn't break out LDC. What he does is he puts this in this equation and simplifies it. But I like doing this, because this is something you should know. I mean, it should be like ethical MA kind of knowledge. This is the way I think about it, because I know it's proportional to skin depth over radius A. Follow me? So that's a wire, just a wire by itself. Has that internal inductance at high frequencies, and that high frequency actual resistance, the resistance changes. That's just the wire. After you talk about a wire, the next thing you have to talk about is what do the individual elements, or most commonly saying capacitive elements, look like. Capacitors, inductors, and resistors at high frequencies. And this is important. The first time I really appreciated this, I got, you might say, an education the hard way. We had to do a senior design, and we had, but a guy taught us in it. We took a CB radio. You all know what CB is? Citizens Band Radio. Truckers use them all the time. We turned that into a ham radio. So we altered the transmission frequency. Right? That's high frequency internet. So what we had to do is we had to change the oscillators, and in doing so, we had to go in and unsolder and resolder and then re-engineer the circuit. There's more to this than I'm saying. Well, at high frequencies, even if I put my finger in there, it changed the resonance. I found that. And this is very troubling. So we had to get dielectric screwdrivers. We had to calculate the inductance. Everything had to be precise, and we had to put in for adjustable values. They're called potentiometers. We had adjustable values for the inductors and capacitors, so we can actually tune it to get the exact frequency that needed to be for transmission on each thing for a ham radio. A ham radio is about 10 meter band, I think is what we used. If you think about that, at 300 megahertz, at 300 megahertz, that's 1 meter band, right? At 30 megahertz, that's 10 meter. 30 megahertz isn't that high frequency, if you think about it. When you're doing engineering into the gigahertz, that's microwave, 1 to 5 gigahertz, this problem becomes much worse. So I'm just telling you, what I'm showing you here is something you have to be keenly aware of when you're doing any kind of modifications in engineering at that frequencies, especially the final product that you're trying to get out the door. Just be aware of this. So that's for wires. Now we're going to talk about components. The first one is the good old resistor. This is in his book. I think the next thing he does is resistor. You just do the wire. We didn't even talk about how much energy a wire, or I should say the radiation resistance of the wire, because frankly, if the wire has any significant radiation resistance, you got a much bigger problem, because that means you're radiating a lot of energy. You're creating energy. So the next thing is the resistor. So the symbol for a resistor, the usual symbol, I mean, this is the symbol used by all the engineering world, R. And resistors can be anything. They can be, you're used to these carbon resistors with bands on them, right? And you have to, black, brown, orange, I haven't done this in a while, but you can read them from the color coding on them. And they have a tolerance, but if you think about it, you got leads, you got a chunk of carbon, and that's one type of resistor. There are so many types. When you're building like VLSI, very large scale integrated circuits, they can have a resistor that actually is a serpentine pattern. They can have a resistor that's a spiral resistor. They can make it any shape that they want. You all follow me? The model for this resistor, if it's just a carbon resistor and it looks like this, there are all sorts of different models. It looks like this. What they usually say is, you always start with a basic component. Now all elements, either inductors, capacitors, or resistors, at low frequency look like what they're supposed to. They look like the resistance, or the capacitance, or the inductance, at low frequencies. But as frequencies go up, things change. So when you have a resistor R, that's what it looks like at low frequencies. But then there's something that happens. Because you're going to develop a voltage across there. You all follow me on this? Anytime you have a difference in voltage between 2 points, you have charge buildup, positive and negative charge. When you have that, you have effective capacitive energy. So they model this by a capacitor. And they'll call it C sub P because it's parasitic. First of all, we don't want it there, but it's there. It's a parasite, you might say. So it's a parasitic capacitance. But we also have metal leads. They're made usually of copper. Anytime you have any length of lead, you have an inductance. You can't get rid of it. It's an internal inductance plus an external. So normally when they model this, they'll also put L, it'll be of the lead. And that would be the model for a resistor, right here. That's truly what it is. So if you wanted to take a look at Z input for this, the input impedance of this right here, and we can do this in the S domain, you would have, well, the impedance of the inductor is what? It's just SL, right? The impedance of the capacitor right here is 1 over CS, right? I'm just, do y'all follow me? S is really what? Sigma plus J omega. You have the Laplace transform, right? But we normally do it with S with analysis. So we could say the actual Z of the resistor itself would be S times L. And I'm not even going to put, L lead here. It's assume that. Plus, and it would be the parallel combination of the resistance and that. So it would be 1 over R plus SC. I just took 1 over resistance plus 1 over the impedance of that, which would be 1 over CS is just CS. Do y'all follow me on that, guys? Everybody follow me how I wrote that and why I did it? You can think of it this way. S is just J omega. You can leave this J omega. Okay. Probably the next thing I'll do is say we can modify this somewhat. If we multiply this, the SL plus, and then we can multiply top and bottom. Actually, what we can do is divide by top and bottom by C. So then I have 1 over C over S plus 1 over RC. And then after that, we can go ahead and get a common denominator if we want. Do y'all agree with that? We can go ahead and say this is really going to be equal to S times L times the quantity S plus 1 over RC plus 1 over C over S plus 1 over RC. And then square the thing out, so you have S squared L plus SL over RC plus S times, what is it? No, plus just 1 over C, pardon me. All over S plus 1 over RC. I did it this way for a reason. I wanted to make sure this S had no coefficient other than 1. So this is going to be a useful point. Y'all follow me on this class? This will be a pole right here. And you can manipulate this to your heart's desire. As a matter of fact, usually right up top, they'll take the L out in front here. And then you're going to have S squared plus, and it'll be S over RC plus 1 over C. Actually, let me just write this here fine. So they'll take an L out in front. Then they're going to have S squared plus S over RC. And then it's going to be plus 1 over LC here, all over S plus 1 over RC. So the only thing I'm doing is showing you a way to manipulate this thing so we can actually talk about a plot of it. A plot of the impedance. This is important. So that's the impedance of a resistor. Now, I'm gonna just let you know a couple of things. When you do this at first, you've done this a few times. We can factor this depending on what R and C are and L, right? And you can either have complex poles or just both real poles or a double pole. Y'all follow me on that, class? You don't know yet. But one thing for sure is I'm going to have the 1 over RC here times S and 1 over RC down here. And here's what this looks like when you plot it. When we talk about really doing EMC work almost always we're gonna use logarithmic plots, and what we do is they're Bode plots. So we use Bode plots, and on the vertical axis, if it's related to voltage or current, which resistance is proportional to that, it's 20 times the log of the magnitude of the impedance on this axis. And then on this axis is the frequency, F. And it's logarithmic down here, so it would look like, this would be like 1, 10, 100, 1,000, and so forth. Y'all follow me? So it's gonna be a log scale down here, log F down here. And it's 20 times the log of the impedance. Y'all follow me? So when you have a resistance, you have any resistance, and you plot this right there, here's what happens. At low frequencies, it looks like just the resistance. So this value will be 20 times the log of just R. You can forget everything else, because look, if you take a look at this equation, when S goes to 0, what do you really have? When S goes to 0, this top part goes away, that goes away. I have 1 over C times 1 over RC, flip that, you get R. As S goes to 0. Y'all follow me on that? It's just R, so 20 times the log R. Then there's the first break frequency, I call it, right at this point. At this frequency, and I'll tell you where this is, so you can actually follow along.
It's page 509.
Okay, so the first break frequency is going to be this pole here. Now remember, when this becomes apparent is when S is equal to 1 over RC. Y'all follow me? At that point, then you start falling down about 20 dB per decade. So since S is really equal to J omega, is equal to 1 over RC, when you take a look at the magnitude of this, really magnitude that, magnitude that, magnitude that, you get 2 pi F is equal to 1 over RC, or you get the frequency, this is the low frequency break frequency, is going to be 1 over 2 pi R times C. Now right down here, the first break frequency is going to be 1 over 2 pi R times C. If we were plotting versus omega, it would just be 1 over RC, but usually they plot versus F. Then the resistance starts coming down, or the impedance, I should say, at minus 20 dB per decade. Follow me? And it keeps going down until it hits the resonance. And this is the resonant frequency, F resonance. Now, the way you get resonance is you set this term equal to 0. Do y'all remember how to calculate resonance? When you had a series circuit, right, resonance was the point. If you just had an LC circuit in series, at resonance, the impedance goes to 0, right? We don't have quite that. We have an impedance. We have a capacitor and a resistor. The capacitor is in parallel with the resistor. It won't go that far down. But the resonant frequency, do you remember what the resonant frequency is for an LC circuit, either series or parallel? This is one you should keep in mind. Anybody? Resonant frequency is always going to be equal to 1 over 2 pi square root of LC. And this would be, of course, the leads and the parasitic capacitance. Do y'all follow me on that? Then it hits the absolute minimum. And then, after that point, it starts coming up at 20 dB per decade. Now, this isn't exactly true. Remember, Bode plots are used to approximate the actual characteristics of a circuit or characteristics of a solution. In truth, if you look at his book, even though he has a logarithmic plot, he does it the right way. If you look at page 509, you see that those are more gradual, right? But the way it's usually approximated and shown, and the way you actually do analysis, is you'll do a Bode plot, and from the Bode plot, by looking at that, I can tell when I'm in danger, when I have to really be careful about things. Because if I'm down at this frequency range, I don't worry. Resistance looks like resistance, like it should when I did the initial engineering. But if I'm pushing the frequency up to here, all of a sudden I know that resistance, if it's used to bias a transistor or something, it doesn't look the same anymore. Things are changing in a bad way. And I get out here and things are just disgusting. Because now, it's instead of resistance, I'm getting an impedance that could go up orders of magnitude beyond what I want. Do y'all follow me in this class? You need to be aware of that for any type of resistor. And I'll tell you this much. Anytime you do any kind of real work in designing circuits, cut the lead links down as short as possible. Try to make them as short as possible. You want any kind of lead length that's substantial is a real thorn in your side, in your flesh, when you get up around a gigahertz. It's absolutely horrible to work with. Follow me on that, guys? I'm just trying to tell you from practical experience, make your lead links as small as possible, use the smallest amount of solder that you can, and whenever possible, I always tell people, go to coax cable for anything, because coax, believe it or not, is very good for making things EMC proof, and it also, as far as a skin depth problem and things of that nature, it minimizes the effects. Okay, that's a resistor in a nutshell. And I haven't done this long. I can go through a practical example and show you exactly the characteristic frequencies, but the minute you have the parasitic resistances, the parasitic capacitance and the lead length, or the inductance of the lead, you can draw that plot, and you can estimate the value of resistance for the impedance. Y'all follow me, guys? Okay, next, we're gonna look at a capacitor. And there are a lot of different kind of capacitors out there. You know those little flat disc capacitors, microcapacitors? There's ceramic capacitors, do you know what I'm talking about? Dielectric is mica or something like that. Those are very common. Anybody ever made a capacitor in physics? Well, I can't say I actually made this, but this is the typical. You take aluminum foil, take about 3 foot length, 3 foot piece of aluminum foil. Then you put a piece of wax paper over the top. It has to be slightly larger so you get some wax. You know what I'm talking about? Like the wax paper that or whatever they call that.
Parchment paper.
What is it?
Parchment paper.
That's fine. Yeah, but it's got to be dielectric. Just put it on top. Make sure it's slightly larger. Then go ahead and put down another 3 feet of aluminum foil. Now you got a sandwich, basically. Believe it or not, that's a capacitor. Then what you do is, and you have to do this carefully, you have to have an attachment point to the outer aluminum that's isolated from the inner aluminum foil. Then roll it up into just a tube like that. And believe it or not, now you've got a capacitor that's actually you built it the way actually real capacitors are built. That's a parallel capacitor. And you can estimate the capacitance by taking if you think about capacitance for proportional surface area, so just the area of the aluminum foil, inversely proportional to separation distance, so figure out the thickness of your wax paper or parchment paper, and then multiply it by epsilon naught times the epsilon relative of the parchment. Now wax paper is about, I think, 2, I actually don't know what some of these are, but it's about 2 to 3. It's not super hot, and you'll have a capacitance. You can estimate if you actually measure it, you'll find out you're almost nailed. So that's making a capacitor just to show. I guess you would get this in probably grade school physics or in grade school, high school physics, something like that. It's a simple thing that makes people appreciate. By the way, you can charge that sucker up until it arcs over if you want to hear it bang. kids like that. And then you can also charge it up and discharge it, in like even one of these small wattage light bulbs in a flashlight. You can touch it, and once it's charged, it'll flash just for a second. Oh, wow. Kids like that stuff. So, I haven't done that, but if you look on YouTube, you'll probably find it. That's the one thing. YouTube is really the internet, but specifically YouTube has more useful stuff about how to do things than anywhere else. I mean, I couldn't imagine that when I was a student having that available. Do you know the concatenating guys? You know what that is? That guy is phenomenal. The amount of information he's out there. Okay, so now we talk about a capacitor. And what it looks like at high frequencies at H. So this is a yield capacitor, and there's so many different types. There's microcapacitors. There's one in particular capacitor you need to be aware of. Do you know what an electrolytic capacitor is? How many do? One person? Only one.
That's the big one, like that.
Electrolytic capacitors are interesting. First, they're filled with usually a gooey liquidy thing. It's kind of a thing, but it has a very high dielectric constant. And it's got a decent arc over it. However, the substance that they use as dielectric is ionic. And once it's polar. When you go ahead and put a voltage on there, all the poles, dipoles will align in a certain way. And if you try to send current through it in the opposite way, in other words, get a true AC current across it, the poles will try to move. And when they do, it causes heating. It causes a lot of heating, and it'll blow up. So with electrolytic capacitors, and they are lossy, by the way, you have to only use like DC voltage on it with a ripple. That's what they're used for, is basically rectification. You guys don't have this experience, but I've seen what the aftermath of some of these blowing up, especially big ones. It's scary, it's a grenade. I mean, it can kill you if you're in the room when one of these things go off. And I'm talking about like the 250-pound capacitors. But anyway, in general, capacitors are energy storage devices primarily. They store electromagnetic energy by separating charge that's near each other. So when you have a capacitor, the real model that's commonly used, and this isn't a good model for electrolytics, but for all the other capacitors, is you got a capacitor. As frequency goes up, you've got a lead length, so you're always going to have some L lead, right? And then anytime you have wire, you also have a resistance. So they'll have some R associated with the internal resistance of the capacitor and the lead. It'll be R parasitic. This is usually the model given for most capacitors. Now, we're going to get Z into this in a second. I want to say one thing. When you have electrolytic capacitors, there'll be a resistor right here because they're very lossy. I'm just telling you that. But normally, for microcapacitors, for most standard capacitors that are out there that are used in electronic circuits, that resistor doesn't exist, and you have this. So when you look at this, the impedance of this, Zn, well, those are in series, and you know the impedance of an inductor is just S times L. The impedance of a capacitor, 1 over CS, and the impedance of a resistor is just resistance. So now you have SL plus 1 over CS plus R. They're all in series, right? Now you can go ahead and I'll start by multiplying everything by CS, so I get simply S squared L times C plus 1 plus S times R times C. And this should look vaguely familiar to you. And then what I'm going to do is first divide everything by LC. So I have S squared plus 1 over LC plus, and then it's going to be S times R over L. And typically it's rearranged like this, S squared plus S times R over L plus 1 over LC. And that's the impedance. Now, does that look vaguely familiar to you at all? From signals and systems? It sure does. As a matter of fact, this, if it's factored, will have either a double pole or it will have two separate real poles. And there's three possibilities for this type of circuit behavior. One is overdamped. That's where you have two distinct poles that are both real. Then underdamped, right? That's where you're gonna have poles that have imaginary components. And then critically damped, that's when you're at resonance. You have only one pole, but it's a double damp. Do you remember sort of this stuff? Okay. Now, if you actually plot this, since this is the input impedance, this is what you get in that plot. This is going to be frequency, and it's the log of F on this scale, log of F. And here it's 20 times the log of the magnitude of the impedance, the N. And this is for a capacitor. So, well, what's the impedance of a capacitor at DC, anyway? One over CS, right? It goes to infinity, right? As S goes to 0, S is J omega. As frequency goes to 0, 1 over 0 is infinite, right? It's coming in from infinity, and it's coming down at a rate of 20 dB per decade. So it's coming in at minus 20 dB per decade. Maybe I better talk about this in a second. Then it's going to keep coming down until it hits the resonance frequency. And the resonance frequency is the same for all inductors, capacitors, and resistors. It's 1 over 2 pi times square root of L, and that would be the lead L, times, I'll just put LC there, L times C. It's really, C is the value that's stated on the capacitor, and L would be the lead impedance. And then after that point, it goes up at a rate of plus 20 dB per decade. Now, I guess it's worth me saying this. What I mean by 20, why do I say 20 dB per decade? Or 40 dB per decade? Let's just take the impedance of a standard capacitor. That's 1 over SC. Does everybody agree with that? Now, if we're going to plot that versus frequency, this would actually be equal to 1 over S, which is omega times C with the J in it. And if I took the magnitude of that impedance, it would be 1 over, and I'm going to do it with frequency, it would be 2 pi, or I'll do it with omega. 1 over just omega C, right? I'll leave it in terms of omega. Now, I'm going to take 20 times the log of that. So 20 times the log of the magnitude of Z, and that would be the actual impedance of the capacitor, in dB, would be equal to 20 times the log of 1 over omega C, which is really minus 20 times the log of omega C, which is minus 20 times the log of just C minus 20 times the log of omega. Y'all agree with this, class? Now, if you just plot versus frequency, let's say I'm here at, just call it 10, and I look at this plot. I know I have minus 20 times the log of C. That's a constant, right? It never changes, correct, class? This is minus 20 times the log of omega. So if I'm at this point, I'm going to have a certain value. It's going to be minus 20 times log of C minus 20 times log of omega at that point. Now, if I go up my order of magnitude, you can see here, if it was 10, I have 20 times the log of 10 is going to be minus 20. Do you agree? Now when omega goes to 100, that's an order of magnitude higher, I have minus 20 times the log of 100, which is 2, and this would be minus 40, or it would go down by 20 dB. So from there, at this point, now this would be a total difference of 20 dB, and it would be over a decade or an order of magnitude in frequency. That's why we talk about things going down 20 dB per decade. Y'all follow me? If the impedance wasn't proportional to omega, say it's proportional to omega squared, if this is omega squared, then what happens, it would go down by 40 dB per decade, because if you have 20 times the log of omega squared, the 2 would come out in front, it would be minus 40 would be the coefficient. Then it would go down as minus 40 dB per decade. Do you all remember this stuff? Seeing it before? How many do? You guys, did you have this? You did? You should have had signals and systems. I don't know if you remember. Voting plots are very important, and you have to appreciate what they mean. Why it's 20 dB or 40 dB or 60 dB per decade is really has to do with the exponent on the highest power of omega. And in this case, if it's omega to the first power, which this is, it just is going to either go up or down by 20 dB. If it's squared, 40 dB. If it's cubed, 60 dB per decade. Y'all follow me? That's just something to appreciate. So that's the reason these plots are the way they are. These are 20 dB per decade because early on a capacitor looks like a capacitor. I just showed you it falls off as 20 dB per decade. Once it hits resonance, then it starts going up at 20 dB per decade because there's an S squared that's interacting with a 1 over S terms, and effectively it means it's going up as S. And if you actually look at the impedance, this is sort of self-fulfilling, but that's what it will look like. And this should be in Limper's books too, but let's see where it is. Capacitor, does he have this plot down there or not? He doesn't show this plot, I don't see it. But I remember that plot. Finally, when you talk about, oh no, he does. He has one on page 515 at the bottom. Now for the inductor. Whenever I hear the term inductance or inductor, I usually think of coils of wire. And most inductors that you're going to find, you run into in circuits, have tightly wound coils of wire. So an inductor, if you think about it, if you have a tightly wound coil of wire, I'm going to try to draw this like this. And this is my inductor L. One thing you got to realize, that there's a voltage difference V across the top to bottom, and it's an AC voltage, all right? That means there is a small but measurable voltage difference between this point and this point, or there is an effective capacitor per winding. There's a capacitance per winding. Think about that just for a second. Does that make sense to you? If you have, there's got to be a voltage difference between top and bottom, and since there's many turns, there has to be a slight voltage difference between the first turn and the fifth turn type of deal. And if there is a voltage difference, there will be a charge distance, which is an effective way we model as with the capacitance. So when we talk about an inductor and a high frequency model of it, we start with a simple, just draw an inductor L. That's the thing you pull off the shelf, it's got a value. Now, an inductor will have a capacitance associated with it. And the capacitance is usually, well, the way he's going to show it, it should be this way. And there will be some finite amount of resistance, R. And that's R, and this is just the wire. And this is C parasitic. I'm gonna take a look at the model he has, because there are higher order models. He also adds the inductance of the lead. Sorry, I'm looking at the wrong one. Take it back. What he does is this. He's gonna put the resistance here, that's probably actually better. He's gonna have an R there in parallel with this inductance. Well, this will work, but that's not quite true. Usually there is some finite resistance in series with that inductance too, but anyway, he calls this R of the leads as such. This model is not bad though. So, if you look at this model and look at the impedance for a second, you can see that really the impedance of this is SL, right? And the impedance of this would be 1 over CS, and the impedance of that is R lead. So if you take a look at this, Z end of this would be equal to SL in parallel with 1 over CS plus R lead, right? Okay. If it's in parallel, I can say it's 1 over SL plus 1 over, I'll just call it R plus 1 over CS. Y'all follow me on this? Now the fun begins. I just want to get something where I got a numerator and a denominator that are polynomials. So I'm going to start by multiplying everything top and bottom by S, and I get S. Then I get 1 over L plus S over R plus 1 over CS as such. Actually, I'm going to do it a different way. Erase this. I'm going to multiply top and bottom by R plus 1 over CS. So I have R plus 1 over CS over, and that's going to be 1 plus R plus 1 over CS divided by SL. I'm going to do it this way. Then I'm going to multiply top and bottom by SL. So then I get S times L times R plus 1 over CS over SL plus R plus 1 over CS. Then multiply everything by S again, so I get S squared, SR, and just 1 over C there, S squared, SR, and 1 over C there. And then I can divide by L if I want, top and bottom. And if I do that, then I get divided by L and L here. And that would be the final form of the equation. Now, the roots of that are where the poles exist. I'm going to grab the actual plot of this and give you a clue. This is in his book, but for an inductor, the Bode plot of 20 times the log of the impedance of the inductor versus F looks like this. It's going to come in at zero. It's coming up at a rate of 20 dB per decade. Then it's gonna hit resonance, and F resonance is just equal to 1/2 pi square root of L times C. And L is the inductance, and C is the parasitic capacitance. And then it falls off at minus 20 dB per decade. Now, I'm gonna just mention one thing about this. This is the inversion of the capacitor's impedance, if you think about it. For a capacitor, came in from infinity, hit resonance, then starts going up again, right? For an inductance, what's the resistance of an inductor DC, or impedance of an inductor DC, ideally? It's a zero, right? I mean, impedance is J omega L. If omega is zero, it's zero, right? It comes in at zero, increases at 20 dB per decade, hits a relative maximum at resonance, then starts falling off. It's the inverse. But just take the capacitor curve and flip it upside down, you got the inductor curve. Follow me on that? And it should make sense to you, because capacitive reactance is 1/SL, inductive reactance is SL. They should be inverse. All right, that's enough of that. Now, give you a quick. Can you do me a favor? First row, populate, you stay there. Empty this row, populate this row, empty that row, populate this row, empty that, well, yeah, populate this. Thank you. Please make sure you put your name on it. As closed book, closed notes, no wearable electronics to you. But do make sure you put your name on it.